I find it very, very easy to be true. I find myself alone when each day.
Hello everyone, welcome back. Today we're going to be looking at how two lines can intersect and interact in 3 dimensions. So we'll be talking about the intersection of two lines in R3. And to start with, we'll take a look at this problem. Does line 1 intersect line 2? I have 2 different equations of lines there. When we're looking at this equation, we need to take a look at how we're using 2 different parameters with our direction vectors. So in line 1, I'm using the parameter s. In line 2, I'm using the parameter t. And the reason why we need to take note of this is because we can't assume that s is going to be equal to t. Okay, these are going to be different scalar multiples. They're going to have different values depending on how these lines intersect. So we can't assume that s and t is equal. So as we're trying to figure out if these lines intersect, we also need to remember that lines can be parallel in R3. I can have 2 lines in 3 dimensions that are parallel to each other. So I need to, first things first, check the direction vectors. And I'm looking for whether or not my direction vector, -1, 1, and 4, is equal to some scalar multiple of the other direction vector, -6, -1, and 6. And while I'm looking at this, it's easy to realize that no k value exists that makes this true. So we can say that line 1 and line 2 are not parallel. Since these are not parallel lines, we can move forward with checking to see if they do intersect. So now that I've verified that the lines are not parallel, the second thing that I'm going to do is convert each equation of a line to parametric equations. So for line 1, x is going to be equal to -3 minus s, y is going to be equal to 1 plus s, and z is going to be equal to 4 plus 4s. And for line 2, x is going to be equal to 1 minus 6t, y is going to be equal to 4 minus t, and z is going to be equal to 6 plus 6t. So I've converted each line to its parametric equations, and now for my third step, I'm going to select any 2 parametric equations, or any 2 components, and I'm going to equate them. I'm going to set them equal to each other. So I'm going to take my equations for x and y, and I'm going to set them equal to each other. So negative 3 minus s is equal to 1 minus 6t, and 1 plus s is equal to 4 minus t. And the reason I'm doing this is that if there is a point of intersection with these two lines, the x component and the y component for each line will be equal. And likewise with z, but I'll get to that in a minute. So I've set these two equations equal to each other. So now I'm going to rearrange this so that all variables are on the left-hand side and all numbers are on the right. And once I've rearranged this, if I look at this set of equations, if I think back to grade 10, there's a method of solving equations called elimination, where we can add or subtract equations to each other to get rid of a variable. And I should notice that if I add these two equations to each other, my variable s will disappear. So if I add these two equations to each other, I get 6t plus t, I get 7t, negative s plus s is 0, and 4 plus 3 is 7, so I get 7t equals 7, or t equals 1. And I can then take t equals 1 back into one of my original equations to find my parameter s. So if I take this and sub it into my equations for the x variable, I get negative 3 minus s equals 1 minus 6 times 1. Rearranging, I get negative s equals negative 2, or s equals positive 2. And now that I've solved for s and t, I'm going to sub s equals 2 and t equals 1 into the original 6 parametric equations. And this will show me what the point of intersection is. So for line 1, my x parametric equation was x equals negative 3 minus s. Now this would be x equals negative 3 minus 2. That equals negative 5. My y parametric equation was y equals 1 plus s, or 1 plus 2. That equals 3. My z parametric equation was 4 plus 4 times s, or 4 plus 4 times 2. So for line 1, using an s value of 2, I get a point of negative 5, 3, and 12. If these lines do intersect, when I sub t equals 1 in for L2, I'll get the same values, and it looks like that's what's happening. So my y was 4 take away t, or 4 take away 1. That equals 3. Z was 6 plus 6 times t, or 6 plus 6 times 1, which is 12. And look at that. negative 5. I get the same values for line 1 and line 2, which means I can say the point of intersection for line 1 and line 2 is at negative 5, 3, and 12. Okay, a second example. Same question, we want to look at and see if line 1 intersects line 2. So again, the first thing we should check and see is if the direction vectors are scalar multiples of each other. And if you inspect this, you should notice that if I multiply 5 times 3, 5 times negative 3, I get negative 15. If I multiply 4 times negative 3, I get negative 12. So there is a k value that makes this true. Which means that the lines are parallel. They have different starting points, but they point in the same direction. So since these lines are parallel, they have different starting points and they point in the same direction, we can conclude one of two things. They're either going to have no intersection, or they're the same line and they have infinite intersection. So there's a way we can check this to see if there's a distinction between the two. And we'll do that in example 3. Here I have two new lines, line 1 and line 2. And just by looking at this, I should notice that I can multiply the direction vectors by 2, and they'll equal each other. So these lines are parallel, but we want to check and see if they intersect. And we're going to do that a slightly different way this time. I am going to take my x components, so 4 plus 3t, and I'm going to set them equal to each other. So 4 plus 3t equals 7 plus 6s. We'll call that equation 1. Equation 2 will be my y components. So 1 plus 2t is equal to 3 plus 4s. And equation 3 will be my z components. 3 minus t equals 2 minus 2s. And I'll rearrange these equations so that all my variables are on one side and all my numbers are on the other. And once I've done that, you may notice something. You may notice that in the first equation, there's a common factor of 3. And if we reduce the first equation by dividing all terms by 3, I get t minus 2s equals 1. In the second equation, there's a common factor of 2. If I divide out 2 from all terms, I get the equation t minus 2s equals 1. And in the third equation, if I divide all terms by negative 1, I get the exact same thing my original equations, this means something. All of these equations are equal. And when this happens, that means our two lines are coincident, or they're the same line. Which means there's a line of intersection. And to describe that line of intersection, I can just pick any of the two lines that we started with. So my line of intersection is the line 7, 3, 2 plus the parameter s times the direction vector 6, 4 and negative 2. So today, in this video, we've looked at three types of ways that lines can interact with each other. There can be a point of intersection. The lines can be parallel and never intersect. Or the lines can be parallel and intersect an infinite number of times because they are the same line. In class, tomorrow, we're going to look at one more way that these lines can interact with each other. Please bring your questions to class.